Welcome everyone to our Scaling Networks ITC course meeting for the week of 10-12 or the day of 10-12-17. I appreciate everybody being here. Today we're going into chapter 3 of our scaling course, which is going to be looking at spanning tree and LAN redundancy. One of the things we need to really think about as we're going into this particular activity is remembering how switches work on a network. Now let's kind of review this a little bit. If we look at a network and we think about a switch, by default, how does a switch handle a broadcast?
By default, it sends it out all the ports.
It sends out all ports except the port it came in on.
Yeah.
Also, remember switches build MAC address tables, so they build tables of MAC addresses using the source frame MAC address as it comes into a port. So they're going to be building these MAC address tables as frames go through each individual port. They will also use those frame information in the MAC address table to send items directly between two hosts. So for instance, once switch 2 actually learns about the devices connected on its ports, if PC1 sends something to PC3, that will come in. Switch 2 will see the destination MAC address and will automatically switch it over to port F06 and send it out. So that's really good. The problem comes in when you look at redundancy in a network that is a layer 2 network. This particular slide here just shows communication going straight across this trunk. So this is a direct unicast going across and back, which wouldn't be a big problem, but the issue you will have is, and this is showing you redundancy, you have this link goes down, this other link comes up. That's a great thing, and that's exactly what we want. In other words, we want redundancy in our cabling, and we want layer 2 redundancy, but we cannot have loops, because if we have loops, we can have what's known as MAC database instability, where switches think that MAC addresses are on 2 different ports. We can have broadcast storms, and those are really, really bad. We've inadvertently caused broadcast storms in our virtualized environment before, and it's very bad. You go back there and you look at all the switches, and the switches just have blinking lights and amber lights, and it's just nothing will communicate. So that's not good at all. Or you can have multiple frames being received at a destination, and that could be a big problem. So what I'm going to show first, I really want to show the broadcast storm. So by default, if you didn't have some mechanism, when a broadcast went out, it would go out all ports except for the port it came in on. And then it would just continue to do that and continue to build. Because remember, the destination MAC address on a broadcast is all Fs. So this storm would just propagate. And there are no layer 2 time to live features. So instead of eventually stopping like it would at layer 3, because layer 3 has a built-in time to live. So even though you can cause loops in layer 3, it will eventually stop because of that TTL, the time to live. Layer 2 has no TTL. There's nothing in the frame that is decremented as it passes through a switch. So a broadcast storm is one of the worst possible things that could happen in a network. If this happens, your network's going down. You're going to be unable to send any traffic because it's going to overwhelm your switches. You pretty much perform a denial of service attack on yourself. And I've seen this happen in closets where spanning tree has been turned off, and that's going to be how we fix this, by the way, is with a protocol called spanning tree. But I've seen it happen just when someone accidentally went in and plugged cables in and didn't really know where they were connected, and next thing you know, they're loops, and you've got a mess. The other issue is what's called MAC address or MAC database instability. And with this, a frame can go out and the switch on switch 2 learns where PC1 is, but then it goes out both ports. Okay, so it's going to go out trunk 1 and trunk 2. And when it does that, it's going to go up S3 and S1, and they're going to say, okay, well, PC1 is on 02, this port, and it's on 01, this port. And then as it continues, because it's going to send this out, this is a broadcast, by the way, with a source of PC1. Now, and this is where you really get an issue, S3 thinks that PC1 is off of 01, and S1 thinks it's off of 02, So if anything comes in to S3 to go to PC1, it's going to go across this link, and then this switch is going to turn right back around and send it back. So you've got an inconsistent or unstable MAC address table, a CAM table on a switch. So we want this redundancy, but we want a way for only one side of the link to be up at a time. How are we going to do that? Well, and here's a duplicate unicast frame. This is just where it comes in, hits S2, gets forwarded. So it has no record of PC4. It's going to go out all the ports except the one it came in on. Really, it even goes out that one because it doesn't know where it's at. And here, 2 frames, the same information is sent over to PC4. So what we need to do is we need to fix this. We need a mechanism to allow the physical layer ports to still be available, but not forwarding frames on those ports until a link fails, until there's the loop is broken or the loop is needed to be able to allow for redundant traffic. Now, here's something that confuses people. Because of the way Ethernet works, okay, I want to show you this again. As this frame comes in to S1, then it comes over this trunk 3 and goes to S3, you're going to see it come out on F02. Switch 2 will not receive the frame. It will drop any frame that comes in on 02 because it's in what's called a blocking state. But because this is Ethernet, the switch 3 doesn't really know there's not other hosts on this trunk link. Now there's some expansions to spanning tree that allow us to do a point-to-point and those types of things, but right now, assume it's just standard Ethernet. And so it has to still come out this port. So you're going to learn with spanning tree that you're going to have certain ports that are in a forwarding mode or a designated mode, and you're going to have some ports that are blocked, especially on that redundant link. And we'll talk more about how that happens and everything as we move forward. So here's an example of STP compensating for a network failure. Trunk 1 goes down, STP sees it. It will then bring up the other link, and you have the ability to move through the network through a second layer 2 path. The way that switches keep up with the status of link is by sending BPDUs between switches, so bridge protocol data units are sent between switches. And then spanning tree is going to use the shortest path first algorithm to determine a loop-free path. And we're going to go all over and talk about those. But one of the things I do want you to realize that's a little bit confusing, STP, the spanning tree itself, is considered to be, it's the older standard. So whenever they talk about STP, they're talking about the standard that is associated with, let's see, where's it at down here? I think it's, the 8021D2004, okay? But basically 2004 is where they've renamed it to RSTP. So even though STP is the traditional, original version of STP, spanning tree, RSTP now, rapid spanning tree, is the implementation we use now. It has been actually superseded or has superseded STP. We're also going to learn about a Cisco proprietary version of STP, which is Rapid PVST Plus, and that is Cisco's implementation of STP. So that's their implementation. So it's not compatible with other vendors' rapid spanning or STP versions. So just don't get confused by that. If you see STP or you see RSTP, RSTP is just the version that we are currently using as described by the IEEE standards. Here we see Radia Perlman again. I believe Radia Perlman has done like 90% of the work on spanning tree and a lot of other things we've seen around and about. Very important person in female in the world of computers. So let's look at our RSTP port roles. Now, one of the things that's going to happen in spanning tree is we're going to elect a root bridge. Now, the root bridge, so when we look at RSVP, which is this spanning tree, okay, one of the first things it's going to have is there's going to be an elect a root bridge. Now, how does that happen? Well, what happens is initially all of the devices, all the switches, when they boot up, they actually send out a bridge protocol data unit and say, I am the bridge. And they do that by sending out a BPDU that has a bridge ID in it. And that bridge ID is usually 32768 plus what's called the extended ID. And the extended ID, by the way, folks, is almost always, well, it's not almost always, it's the VLAN number. So by default, on VLAN 1, all the bridges will send out, and by the way, the reason they use the word bridge is a switch is nothing more than a multi-port bridge. That's all it is. Used to be we had bridges that were just 2 ports. There was one segment on one side and one segment on the other. Well, switches are still bridges. They're just multi-port bridges. But at this initial election, all the switches send out a thing that says, hey, my bridge ID is 32768 plus 1, 32769. And they say, I'm the root. Well, if everyone's tied, the other part of the bridge ID is the MAC address. So what will happen is the lowest bridge ID will become the root. So I'm going to do this. Lowest bridge, and here's how I teach my students to remember this. Someone walks up to you and threatens you and says, you've got to jump off a bridge. And they say, it can be any bridge you want, but you've got to jump off a bridge or you're going to die. Now, what I'm going to do is I'm going to find a bridge that's like a foot above the water and jump in the water. So when you elect a root bridge, you want to find the lowest bridge you can find. So the lowest bridge ID. By default, again, that priority is 32768 plus the extended ID. We can change that. We can change it a couple ways. We can literally change the priority of the bridge, or we can use what's called root primary and root secondary, which will cause the priority to drop. It's really important that you try to control your root bridge election, because you probably want your core, well, you don't probably want, you definitely want your core bridges or switches to be the root bridge, so that you don't have to worry about some switch sitting off in a closet that's a 1900 series switch that just happened to have the lowest MAC address becoming your root. All right, so that's the first thing. The next thing that's going to happen is you determine the root ports. Now, root port determination is taken care of by looking at the shortest path to the root, and that is done by looking at a cost that is associated with each port. Now, one of the things you'll learn more about as you move forward is there happen to be 2 links to the root. In other words, port 01 and 03 were both connected to the root bridge. You then look at the priority on the interface. There is actually an interface priority. And then finally, if everything is the same, you actually look at the number of the interface. So F01 on switch 2 would become the root port before F03 if it was connected to switch 1, as long as the actual port priorities were the same. But every single root, we're going to boot up. Everybody says, hey, I'm the root. And then eventually somebody says, nope, I'm the root because I have the lowest bridge ID. In this case, S1 won that. The root bridge won't have any root ports. It always has designated ports. In other words, all the ports on the root bridge forward, for the most part. They will forward, there's no doubt. They're always designated ports on the root bridge. The non-root bridges then determine their root ports. So they're going to determine, hey, what is my best link up to the root bridge? And then we're going to determine the designated, and those are the ports that forward, or the forwarding ports, and the alternating ports, or alternate ports. And those are ports that are in a blocking mode. Okay? So what will happen here, for instance, if you've got switch 3 and switch 2, and they're trying to determine which one of these will be the designated, which will be the alternate, it will look first at the bridge ID. Lowest bridge ID will have the designated port. If that was the same, it would then look at the MAC address, and so, I mean, the MAC address would be part of the bridge ID. So if the priority is the same, then it's going to look at the MAC address. You can also control this by changing the priority on an individual port, so that if there is an actual tie, it can be picked based on that, and then you'll have your alternate and your designated port. Once all of this is taken care of, the switches will send out bridge protocol data units to maintain the spanning tree. And depending upon what kind of spanning tree protocol you're running, there could be a spanning tree instance for every single VLAN that you have. And in fact, S1 could be the root for VLANs 10, 20, and 30, while S3 was the root for VLANs 40, 50, and 60. So the root bridge doesn't have to be the same for all VLANs if you're running a version that uses multiple spanning trees per VLAN, which, by the way, is what Rapid PBST Plus or Cisco's version does. So are there any questions about these roles? Now, there's one more role, and that is disabled. And that would just be a port that was down, that was disabled completely. Any questions on these? Okay. All right, let's move forward then. So here, again, the root bridge, just like I told you, by default, it looks at the priority, which should be the same, 32.768 plus 1 for the VLAN ID. That's where they get the 32.769, plus the MAC address. In this case, you can see the priority has been changed on S1 to ensure that it becomes the root, which, again, is something you should do in your environment. Here's the bridge field again, the bid field or bridge ID. You've got your bridge priority, 32.768, extended system ID, the VLAN ID, and then the MAC address, the 48-bit MAC address. Be aware this is something that could show up somewhere that you would need to know, okay? I will say no more. Once we have determined, again, we've made our election, we've got a root, we've now got to determine the root ports, and we do that by looking at the best path to the root bridge. So we're going to look at the speed of the links, and they will have a cost based upon the spanning tree algorithm. So if it's a 10 gig link, it has a cost of 2. Used to be that a 10 gig and a 1 gig link had the same cost. They've actually revised the cost for spanning tree under RSVP and Rapid PBST Plus so that they can delineate between a 10 gigabit link and a 1 gigabit link. But then you actually go in, you can change that manually if you want to. Be very careful doing this. Have a very good reason for why you're doing it, that you want to shape the traffic to go through using that spanning tree cost, a change in it. So here we got it. We're going to look and we're going to say best pass to the root bridge. Well, if I'm going from S3 to here, all right, my cost is 19. Or excuse me, if I'm S2 and I'm going across this trunk 1, my cost is 19. It's 38 if I go this path. So my best root port is Fa01. Likewise, you do the same thing on the opposite side. This link for S3 is 19, and this link across here is 38. So F01 will become a root port on both S3 and S2. And you can see that here. You can do show spanning tree, and you can see the cost associated. You can also see the role. Okay, so F01 is a root port. Its status is forwarding, and it is an edge port point to point. So it's going to, it knows it's going to another switch. F02 is designated, state is forwarding, again, cost. You'll notice here too that you don't see that this is the root. It doesn't say this bridge is the root. Right? Well, in this one, actually they got this one wrong. They've got the 24. Nope, they do not. That's different. I would say it was the root. That's saying that's the priority of the root bridge it's connected to. And then last but not least, you've got to decide which ones will be forwarding and which ones will be designated. So again, they're going back through here and saying S1 is the root. All right, we know that. S1's ports will be designated because all root bridge ports are designated. S1 and S2 have figured out that these are the root ports. They now need to decide which of these will be an alternate port and which one will be the forwarding or designated port. So you look at the bridge ID, and you will see that the lower bridge ID is on switch 2 because it has a lower MAC address. And because of that, F02 on switch 3 will be the alternate, and F02 will be the designated. So in spanning tree, remember, you want to jump from the lowest bridge. Decisions are based upon the lowest bridge ID, or port priority, or priority, period. Okay? So again, designated versus alternate ports. Alternate ports are, they listen for BPDUs, but they will not accept any frames. They will drop all frames. Now notice here, this is something interesting. S2's root port is F01 that actually goes to switch 4, but that is its best route. Even though it's the same cost across both, it determined that was the best path, and that was partially because of the interface ID in this case. And remember, a root bridge will not have any root ports. Here's looking at the different parts of a 8021D. So this is the rapid spanning tree BPU frame. See the protocol ID, okay? It's all values 0. Version, we'll give you a version on down through, and you don't need to know every one of these, but you can just see these are the different. It does hold the root ID inside the BPDU field, and then it's got the root path cost, the bridge ID, again that's at 32768 plus VLAN plus MAC address, the port ID, and then message age, and down so on and so forth, which you can also see in a Wireshark capture. So that tells you who the root is, the identifier. In fact, this, if I'm not mistaken, this would be the root because you see the root identifier is the same as this bridge's identifier. Yep, that's right. It is, in fact, the root bridge. Now, again, and this is the third time they've shown you this, so it's kind of important. I think you need to know this process. First, you elect a root bridge. Everybody sends out a BPDU and says, guess what? I'm the root. Okay? And they put in their root ID as their number, their bridge ID, and the bridge ID is the same. They basically say, I am the root. They will all look at these BPDUs and then figure out, well, guess what? Switch 1 has a lower bridge ID than me, so I'm not the root. Switch 1 is the root. All right? So it goes through that, and everybody figures it out. And finally, once all this has been exchanged, and it takes a little bit, they will figure out that the switch S1 is the root. By the way, that's why it takes 50 seconds when you plug in a cable into 2 switches. You know, they go amber because they're going through the spanning tree process. They're exchanging BPDUs. That's the same thing that happens when you plug a PC in and you haven't put spanning tree port fast on the port. It doesn't know, the switch doesn't know that you haven't plugged another switch in, so it has to send out BPDUs and try to run through the spanning tree process to ensure that a loop doesn't take place. Once the root is elected, then we determine our root bridges, and then our root ports, and we determine our designated and alternated ports. Here we go again, the third time we've seen this same thing. Bridge priority, 32768, plus the ID, extended system ID. And this was added so that you can do per VLAN spanning trees. All right. And then the MAC address. And here we go with a priority-based decision. So we've got that. And then a MAC-based decision. Notice that if we had let it go to MAC address, the switch 2 would have ended up being the root instead of switch 1 because it had the lowest of the 3 switches MAC addresses. Now, here are the different types of spanning tree protocols out there in existence. 8021D 1998 is the legacy spanning tree. it is now replaced by RSVP, okay, Rapid Spanning Tree, which is our newer version that's out there. There is another version called Common Spanning Tree, which gives you one spanning tree instance for all VLANs. All right. Much more common in use today is PVST Plus or Rapid PVST Plus, which is Cisco's enhancement. In fact, PVST Plus was the enhancement of STP, and Rapid PVST Plus is its enhancement of RSTP, which is an advancement of STP. And I know that's confusing, but here's how you can kind of think about it. Imagine, oop, not that one. Oh, Lord. I have to cut that out now. Imagine this. Let's imagine, okay, in the beginning, there was STP. Cisco developed its own flavor of STP and called it PVST Plus. Well, then they developed RSTP, and Cisco developed Rapid PVST Plus. Okay, so this is basically open standard. This is Cisco. This is open, and this is Cisco. Now, there are a couple other flavors too. You know, there's 802.1s, multiple maps multiple VLANs to the same spanning tree instance. So you can actually do like VLAN 10 and 20 would be one spanning tree instance. 30, 40 would be another. But the big one that we're going to really look at is Rapid PVST Plus as far as configuration. You can look here at the different, you know, Cisco standard, very high resources needed for Rapid PVST Plus. And that is because it is a per VLAN spanning tree instance, but it has a very fast convergence, which is also shared in common with RSTP and MSTP. So, PVST Plus, basically no load sharing is possible. You got one uplink must be blocked for all VLANs. So in other words, you can have routes. The good news is you can share which switch will be the route for one VLAN and another. So you can actually go spanning tree root primary or root primary spanning tree VLAN 10 root primary for VLAN 20, and then VLAN 10 on this switch. It is very nice to use and easy because when you look at the different states, we've got blocking, listening, learning, and forwarding and disable. This is where those 50 seconds are spent during the time when you first plug a cable into a switch and it's amber. It always starts in a blocking state. In other words, it sends and receives BPDUs, but it will not forward any frames. It's also the same state that you have for an alternate port. It then begins listening, trying to figure out what's on the opposite side. Again, still using BPDUs. Sending BPDUs, trying to figure out what's on the other side, trying to do the root bridge election, do the root port election, then the alternated and designated port election. Then it goes into learning, where it can learn MAC addresses, and then finally it goes into forwarding. So that's where that 50 seconds comes from. You know, 15, 15 roughly, and then moving forward a little bit more than that into this forwarding state. So if you ever wonder why it sits there for 50 seconds or so, that's why. And again, we're going through and they're showing the exact same steps yet again. So for the fourth time, I would know these. I would know these the way it works. And then the extended system ID is just used to ensure that you can have an ID per VLAN. So again, this is RSTP. This is the extension to STP. The biggest thing is it is not proprietary. It is open. So if you're running RSTP, you can connect multi-vendor networks together, and they will actually talk to one another. So 802.1W is RSTP. It replaced 802.1D, but it's still backwards compatible. Here's some of the BPDUs, or it just shows you the BPDU inside of RSTP. Still has the learning and forwarding. Okay, you don't really have to learn a great deal about these in terms of these different bits and items for this, but it's just to let you see the BPDU. The one thing that Rapid PVST Plus has on a Cisco proprietary level is it has what's called an edge port. But edge ports are any port that is connected to a non-bridge. In other words, it's an access port. So if you do switch port mode access on a port, you really should put spanning tree port fast on it. The reason being, the second you plug a cable in that port, it comes up. Now, it's still listening for BPDUs. In fact, if it hears a BPDU on a port that has port fast on it, it will immediately go amber and run through the blocking, listening, learning, and then go to forwarding. But if you do this on your edge ports that are connected to hosts, it will ensure those hosts, when the second you plug them in, they'll come up. Okay. Non-edge ports, you don't put that command in because that's where you're going to have to go through the entire spanning tree process to figure out the root and other ports. You can also have different types of links, point-to-point. So we got a point-to-point link between devices. That's a shared link because that's a hub. Hubs are of the devil. Don't forget that. And then these are point-to-point links because they are connected to a single device. Typically with our point-to-point links, we only use that for when it's connected between switches so that we're able to transition quickly into a rapid forwarding state, knowing that we're connected to a switch. You can do that with the spanning tree link type command. We don't do that. When we do it in the labs, we're going to do it there. You'll notice the default configuration on a Catalyst 2960 is that PVST Plus is enabled. Okay, so that is the extension to spanning tree, STP, that Cisco had made. You can enable rapid spanning tree, or rapid PVST Plus, if you want to. We'll show you how to do that. Switch priority is 32768. Spanning tree port priority, this is the priority on a per port basis, is 128. Here's our cost on a per port basis, and then VLAN priorities all the way down to. So you notice hello time's 2 seconds on spanning tree. So BPUs are sent very quickly and in rapid fashion. So if you want to set the bridge ID, you can do it with a priority command. Okay, so you can set it to something below 32768 for the VLAN. So spanning tree VLAN 1 priority, something below 32768. Or if you do the spanning tree VLAN 1 root primary command, this will let the switch actually see all the different bridge IDs out there, all the different priorities that are set, and will set itself lower than anything it sees. So it will set itself to a multiple of 4096 less than whatever it sees on the network. So this should absolutely guarantee that your switch is going to be the root. You can also do spanning tree 1 root secondary, and then this switch would be the secondary root for VLAN 1. This is what is being asked for. I think, Larry, you had an issue with the packet tracer. This is what's being asked for in the packet tracer. So even though this will work, and you will get, when you do a show spanning tree, you will see the correct switches, the correct root. They're asking for this in the packet tracer. So if you don't do that, it won't give you the points. Very important you know how to do these because you're going to be asked to do that in the labs, and you're also going to be asked to do that probably on the test. So show spanning tree, this bridge is the root. That lets you know it is the root. Okay. And port fast, BPU guard. One of the things you want to do is put port fast and BPU guard on these ports. Now, what is port fast? That's the edge port command. So that's basically making it a spanning tree port fast. It should only be enabled if you're connected to a single host. Now, spanning tree BPU guard enabled. What this does is, if it sees a BPDU, it will cause the port to go down and make you aware of that. Because what has happened is someone has placed a switch onto what should have been a host-only port or an access-only port. And you can see those in the running config when you add them into the switch. And don't forget the interface command, because you can, the interface range command. So, if you've got a series of ports that you want to all have the same commands on them, use the interface range command to make it easier. This port fast is important with items like DHCP, where a host may send out a DHCP request. So make sure you enable that. But you also have to be careful because If you accidentally connect the switch, if you don't have BPU guard, it will still would go down eventually because it would go in that state. But if you put BPU guard on it, it will actually air disable the port and cause the port to go into an disabled state that you can then go see why. And it'll say it's because of BPU guard, which tells you somebody accidentally plugged a switch into an access port. This is they say load balancing, it's really not, quote, load balancing. It's just making one switch the root for one VLAN or one set of VLANs, and then the secondary for another set, so that you can have it, if one of the root bridges goes down, it can take over. So in some ways you're load balancing because you're not putting all of the root responsibilities on a single switch. Okay, so you can go spanning tree root 20 or VLAN 20 root primary and make it the primary for 20, and then VLAN 10 root secondary, and it's the secondary for 10, and then vice versa on switch 1, it's going to be the primary for 10 and the secondary for 20. And then if one of those goes down, then you can do it. Now you can also do it this way. You can go in and just change the priority, give it the lowest priority on the network. Personally, I like the root secondary and root primary. It's just easier, and it ensures that's going to take place. Okay. Any questions about that? Any questions about spanning tree at all so far?
No, I'm doing good.
Okay. Everybody, Larry, Scotty, you good?
I'm good. I'm gonna have to go back through it again.
Okay. Well, that's no problem. But so here's one thing we do. We can go in global config. In global config, put spanning tree mode rapid PVST plus. That will give you, or PVST. That gives you rapid PVST plus. Then you can go in the interface, set its link type, and then you can clear spanning tree protocols, and then that will actually reset it so to run through the entire process again. Here we have setting rapid PVST plus, so we can actually put it in that mode. You can see now it says instead of IEEE when it's in RSVP mode, spanning tree enabled. So rapid PVST plus will show inside of the running config. And that's what we're going to run in our labs, is rapid PVST plus. And folks, that's it. We do have a lab, packet tracer lab, and we have another lab. And they got one little thing looking at how to analyze the topology, show CDP neighbors, looking at, try to figure out if it's the correct topology. Show spanning tree VLAN will show per VLAN spanning tree. Show spanning tree will just show you all the VLANs and their spanning tree. And then verify that the topology matches what you're expecting. You know, is it doing what, is the bridge that you wanted to be the root, is it actually the root? Is it not? You know, you can then go look at bridge IDs, look at your election process, see if you've made a mistake. The other thing I will always say too, is it's a good idea to make sure that the bridge that you want to be the root is the first bridge that boots in your environment. That way it will become the bridge, and it won't have an issue with anybody being the bridge before it. Okay. Now, spanning tree, if you do have a failure, you can have especially this one. If you have an erroneous transition to forwarding, this is what can happen to your network. Yeah, it all bursts into flames. Basically, you would end up with a loop. You know, if you had an erroneous transition to forwarding, you would have a full loop, and then those broadcasts, just like a DHCP broadcast, could suddenly cause a storm. So that would be very bad. That could happen in the event that BPUs for some reason were being blocked, but the link was still up. Okay, but it really should not happen. And in fact, spanning tree is not that difficult as far as configuration or use. For a while, they were talking about, a lot of people got away from using spanning tree, and then Cisco came back to, nah, you better use spanning tree, especially inside of your buildings where you've got your VLANs. There's some issues with how big you can make a spanning tree instance. For instance, a diameter greater than 7, because of the way spanning tree works, if the diameter or the number of switches is greater than 7, the spanning tree timers will not work. And so what you need to do is go in with one of the ways you can do it is one of Cisco's technologies. It's called a 3750 switch stack. And you basically put these stack-wise cables in, and then instead of being 4 different switches, this switch now appears as a single switch. Okay? It's got multiple interface, 101, 102, 103. That would be the top switch, all the way down to 2052. Okay? So there'd be 52 ports on each one, and then each one of those would show up, and it would be they are sharing a backplane. So that will do away, instead of having, you know, these 12 switches, you've got 3 stacks. So it looks like switch 1, 2, and 3. And that would fix your diameter problem that you can sometimes have. And that is spanning tree in a nutshell. Our next item we're going to go over is ether channel and hot standby routing protocol, which is a first hop redundancy protocol. But at this point, I'm going to stop sharing. Are there any questions?
Not at this time.
Okay. I'm going to stop the recording.